Hello everyone. I'm going to talk about optimizing VRChat VODs. Now, for those who don't know me, well, I create VRChat VODs for fun, so I release some VODs like VRBomber, Virtual Park, Nucleus, VRBomber is my latest VOD release. So, optimization is a pain. Like, I remember in the past I had to do a lot of research because some of my VODs were performing really poorly. And doing research about optimization is actually pretty difficult because you cannot just Google something like, why do I have 20 FPS? Because there can be hundreds of reasons why you may have 20 FPS. So I had to do a lot of research, reading documentation, watching YouTube videos, etc., etc. So and today I decided to share some of my knowledge I've acquired for the past 4 years. Now, before I start the presentation, I just want to say that you can download the entire presentation, including the Unity project with all my benchmarks on my GitHub account. Here's a link, and you can also scan the QR code if you want to. There's also a Q&A session at the end. You can just ping me on Discord. So my name on Discord is MyroP, same as my VRChat username. And yeah. So before I start talking about Unity, I just want to say that I would highly recommend to learn Blender. The thing is, personally, I like to download assets from the Unity asset store, Sketchfab, or TurboSquid because I'm not a 3D artist. So I like to download assets to save some time. But often I've seen assets that were marked as game ready, but they weren't game ready. And often assets you find on the stores where they're just meant to be used in animations or in rendering. For instance, I once saw this microphone asset, which looks really beautiful, but it had more polygons than some VRChat eBoy avatars out there. Or I once saw a radio asset, which was also really nice, but each button, each knob was a separate mesh, which is also not really great for performance. So if you want to learn Blender, I would highly recommend watching the Learn Low Poly Modeling video by Infanzia. It's the video I watched to learn Blender. What I really like about this video is that he keeps repeating over and over again all the shortcuts you need to know. E to restore, S to scale, I to inset, G to move, etc., etc. And if those shortcuts keeps repeated over and over again, it's such an efficient way to learn all the shortcuts. Now, there are a lot of people who actually also recommend the donut tutorial. Personally, I didn't watch it. But just out of curiosity, I watched it 2 weeks ago, and yeah, I guess I know how to make donuts now. But I would rather, for VOD creation, I would rather recommend watching low poly modeling in Blender. I feel like for VOD creators, it's much more useful. So, now, knowing Blender is nice, but like 90% of optimization happens in Unity. I'm going to start with a very basic example. Here I have a scene with 1 million separate quads, which is about 2 million triangles. Now, when I benchmark it, I notice I had 3 FPS, which is, low. Yeah, it's not a lot of FPS, huh? But then I did one little change. I merged everything together into a single mesh. So now it's one mesh, but still the same amount of polygons. And now I have 1200 FPS. Now, the reason why the scene on the right performed so much better can actually be seen in the top right corner when we click on the Start button. So if you click on the Start button, we can see a bunch of statistics, huh? And we can see on the left I have 1 million batches, and on the right 5 batches. And that's actually the reason why the scene on the left performed so much better. Now, before I explain what the batch is, I first need to explain what a draw call is. So a draw call is like a package that tells the GPU what to render. It includes a bunch of data, like the mesh, the shader, material, bunch of settings, etc., etc. But the thing is, building those packages, it takes a little bit of time for the CPU. Like, it takes a little bit of time for the Unity because it needs to do a bunch of setups, etc. So the more draw calls you have, the worse the performance on the CPU. Yeah? So there are a lot of things that can increase the number of draw calls. For instance, the number of objects and materials you have in a scene. In the previous example I showed, the scene had 1 million objects. That's 1 million draw calls. That's way too many draw calls. Real-time light casting a shadow can also heavily increase the number of draw calls. Yeah? I don't want to get too much into detail about real-time shadows because there are so many things I still want to say, but basically, Unity needs to generate something called the shadow map, and shadow map can, in worst-case scenario, duplicate your number of draw calls. Cameras, they can also increase the number of draw calls because they re-render the scene from the perspective of the camera. That includes also the VRChat mirror, because the VRChat mirror also uses camera to render the scene. Another thing is that it's 1 draw call per material instance minimum. For instance, if you have a mesh that has 2 materials, that's 2 draw calls, and 2 draw calls minimum because depending on the shader you're using, and depending on the lighting environments, can be more draw calls. For instance, if you're using a PBR shader, Usually PBR shaders, they get rendered in one draw call. But the moment there's a real-time light source in the scene, like a point light or a spotlight, then that material gets rendered in 2 draw calls. It's basically one additional draw call for each pixel light in the scene. So if you have 2 point lights in the scene, that's 1 draw call to render the PBR shader plus 2, so 3 draw calls. Just as an example, if you have an avatar that uses 10 separate meshes, each using 2 PBR materials, and there's a point light in the scene, then it's 10 meshes times 2 materials, so 20 draw calls, but we're using a PBR shader and there's a light source in the scene, so 40 draw calls. If, in addition, that light source also casts a shadow, then you can go up to 50, 60 draw calls. So to reduce the number of draw calls, a lot of things you can do. First of all, reduce the number of material instances in the VRT. Here you can use something called atlasing, trim seeds. You could also work with custom shaders that basically blends between different textures. You can reduce the number of shadow casters. Basically, if you're working with real-time lights, ask yourself the question if every object in the scene actually needs to cast shadow. For instance, grass doesn't always need to cast shadow. In that case, you can, for instance, turn off shadow on grass, and that also reduces the number of draw calls. And also, bake your likes also looks much better if you bake your likes. Doesn't mean that you should ban real-time likes. Real-time likes can look really nice also, but if you bake your likes, you have less real-time like sources, less real-time shadows, and that also decreases the number of draw calls. And there's also another method, which I will talk about the next slide, is batching. So the idea of batching is pretty simple. It's basically combining multiple draw calls into a single batch. So it is a draw call optimization technique, which can also reduce the number of draw calls in the scene. Now, Unity supports several batching techniques: static batching, GPU instancing, but dynamic batching. But I'm not going to talk about dynamic batching because, from my personal experience, it's actually pretty bad performance-wise. And also, Unity documentation doesn't recommend it anymore because it can actually make the performance worse. Now, static batching is actually pretty interesting. So let's imagine you have a tree and a rock in the scene. They both share the same material, but because they are 2 separate meshes, they get rendered in 2 draw calls. Yeah? Assuming we are using a shader that renders the object in 1 draw call. But if you merge both of those objects together, you have one mesh that has a tree and a rock in it, and one material, and that's 1 draw call. And that's the idea of static batching. So to turn on static batching, the checkbox static batching static needs to be checked. But usually, when batching static is checked, we want to check everything: contribute GI, occluder static, etc., etc. Now, first of all, it has a few downsides. First of all, it only works for static objects. Once an object is metastatic, it doesn't move anymore. You cannot move it anymore via scripting, for instance, or via an animator. It creates an additional mesh also. So, for instance, if you static batch a tree and a rock together, what's going to happen is that Unity will keep track of a tree and the rock in the scene. They remain in the scene, but Unity will also create an additional mesh that has the tree and the rock in it. That increases build size and also memory usage because you have just an additional mesh. It can cause issues if a mesh uses a vertex shader, for instance, a billboard shader. Now, how billboard shaders work? It's basically a shader that rotates the vertices around a pivot point. The pivot point is usually just the origin of a mesh. And this is to basically make sure that the mesh always points towards the player. But the issue is that when static batching is turned on, that pivot point moves to a different location. And you will get that weird issue where suddenly you see billboards floating in the sky or sliding around the scene. Yeah, that usually happens when you also forget to turn off static batching. And it can also happen if you have dynamic batching turned on, also something to be careful about. And also static batching is limited to 64,000 vertices per batch, meaning that once you exceed the 64,000 vertices limit, then Unity will create a separate batch, which also increases the number of draw calls. Now, Unity is not always able to static batch meshes, and here, the Unity Frame Debugger is an excellent editor tool you can use to see why it happens. For instance, here I selected draw calls number, I think it's 62, I can't read. Yeah, draw call number 62, the draw call I just selected cannot be batched with this previous draw call because the object uses a different material. So there are a lot of reasons why batching can fail. If an object has different materials, affected by different light maps, affected by different reflection probes, or if a vertex count limit of 64,000 is reached. In that case, if you have like a lot of draw calls, I would highly recommend opening the Unity Frame Debugger and to analyze each draw call to see why things didn't got batched properly. Okay. Now, to show you how Unity static batches meshes together, I created this scene, which we can see on the right, that has, I don't know, a few thousand spheres. I didn't count it. And I wrote a script that colors each static batch into a different color. Now, the result can be seen in the bottom left corner. Every color represents a separate batch. Now, we can see that it seems like meshes got batched randomly. There's, for instance, a sphere in the bottom left corner that got batched with a sphere in the top right corner. Now, this is not ideal. For instance, if we zoom into one particular part of that image, we can see that a lot of colors, which means that we can see a lot of draw calls. In the bottom right corner, I used an editor script, which I linked above. That static batches meshes by distance. Only the closest objects are batched together. Everything seems much more organized also. Now, if you zoom into the one particular part of that image again, we'll see less colors, so less draw calls. And yeah, that's how editor scripts can improve Unity static batching behavior. It can also improve your number of draw calls. And I would highly recommend trying that editor script out. In my case, that editor script sometimes helped me saving hundreds of draw calls. GPU instancing is very interesting. So let's imagine you have hundreds of trees in the scene, and you want to render all those trees. Well, each draw call would basically be render this tree at position A, render this tree at position B, render this tree at position C, etc., etc. So we keep sending to the GPU over and over again the same data, the same mesh, the same material. So it's only the position that is changing. And that's not very efficient. With GPU instancing, we can basically tell the GPU, render this tree at position A, B, C, D, E. So in a single draw call, I'm just sending to the GPU the mesh I want to render, the material I want to use, and the list of position, rotation, and scale in a single draw call. To turn on static GPU instancing, actually pretty simple. In the material settings, you have enabled GPU instancing checkbox, and you just check it. It's really great if you want to render the same object many times. And it has a lot of advantages. First of all, it doesn't generate a new mesh, so it doesn't increase the size of your VOD, doesn't increase memory usage. It works well with vertex shaders, like you can use GPU instancing on billboard shaders. And as far as I know, it's also the only way to batch those billboard shaders. Now, there's no real vertex count limit, contrary to static batching, which has a vertex count limit of 64,000. But with GPU instancing, you can batch up to 1023 instances in a single batch. That doesn't mean that you should overdo it. Don't try to GPU instance 10,000, whatever. But yeah. And yeah, the limit is 1023. The object can also move, which means that, well, basically, to the GPU, you're sending also a list of position, rotation, and scale. And that list can be dynamic, which means that you can GPU instance particles, projectiles, or trees. Now, one drawback with GPU instancing is that objects need to be the same. Okay, you can GPU instance all the trees together, all the rocks together, but not a tree and a rock together. Now, I'm going to show a little example of a pretty interesting use case of GPU instancing. The problem is skin mesh renders. Skin mesh renders are very expensive for multiple reasons. First of all, they're animated on the CPU by Unity before it gets sent to a GPU for rendering. So there's a Unity animator, a vertex that gets moved by the CPU, and then that mesh gets sent to a GPU, and that's not great. Another thing is skin mesh renders. They don't get batched. Never with static batching, nor with GPU instancing. So if you have thousands of skin mesh renders, that's thousands of draw calls. But then, how do some games like FIFA render thousands of NPCs in an arena? Or in some strategy games, there can be thousands of soldiers moving from point A to point B. Let me show you a little example of what I added on my avatar. So this is a dancing chicken. The interesting thing about this setup here is that this is actually not a skin mesh renderer. It is a mesh renderer. And because it is a mesh renderer, I can spawn 5 or 10 of them, and they get batched together because they're GPU instanced. I could also, if I want 100, but yeah, I mean, yeah, you probably don't even see it on the stream. Yeah. I could have even gone, like, if I wanted to, like, render 1,000 of them, but I also didn't want to risk lagging the stream, and even was crushed with theoretic staff teams. That would be pretty bad. So I will try to keep it to 10 and 100. I think that already proves the point. So yeah, VRT is pretty cool. Okay. So how did I do it? Well, basically I used something called the VAT Baker. It's an editor script I found on GitHub, and it allows me to convert an animation file into VIT, vertex animation texture. And the texture can be seen on the bottom of the screen. So on one axis, we have the keyframes. On the other, we have the vertex IDs. Now each pixel we see here is basically the vertex offset encoded into the texture. RGB, XYZ, 3 color channels, 3 axes. So we can store vertex positions in a colored pixel, yeah. Yeah, just a little benchmark comparison, 3600 spree values on the left, VAT 410 FPS, on the right, skin mesh renders 13 FPS. Notice that nothing got batched. I had like 3600 batches on the right and on the left, 10 batches, so most of the spree values got batched together. And we can see that also the VAT version is 30 times faster. And here, just for fun, the entire population of Luxembourg doing the orange justice. So 660,000 spree values. Okay, I have 5 FPS, but I mean, it's 660,000 spree values, huh? And 4 billion polygons. Obviously, I will have low frames, but I didn't try that benchmark with skin mesh renders because, I mean, I think I would have maybe had like 1 frame every 20 seconds, I would assume. And I would like to keep my CPU a bit longer. I like my CPU. So, yeah. Okay, culling. The idea of culling is pretty simple. If there's an object behind me and I'm looking this way, I don't want to render it. If there's an object hidden behind the wall, I don't see it, I don't want to render it. So it's basically skips but doesn't need to be rendering, and that decreases number of draw calls and also gives less work to the GPU. Unity supports a few culling methods: Frustum culling, occlusion culling, and manual culling. Frustum culling is actually pretty easy to set up because we don't need to do anything. It's actually something that is already on Unity, and we cannot even turn it off. Huh? The idea of frustum culling is pretty simple. Everything that is outside of the view frustum, so everything that is outside of the camera FOV, point of view, I mean, doesn't get included in the list of draw calls. Frustum is actually a shape that looks like a pyramid with a tip cut off, and that shape you can see it on the right. But there's one thing we can actually do, and that's playing around with a far clipping plane. So everything that is beyond the far clipping plane of the camera doesn't get included in the list of draw calls. For instance, you can have a VIP area, let's say 2 kilometers away from a spawn area, and if you set the far clipping plane to something like 1 kilometer, well, if you're in the spawn area, you don't see the VIP area doesn't get rendered, and if you're in the VIP area, the spawn area doesn't get rendered, which also decreases number of draw calls and the load on the GPU. There's another cool thing you can do is also play around with the layer curl distance property, which is in the camera component. So basically you can have, for instance, 2 layers, a layer tree and a layer rock. Let's just assume. And using the layer curl distance property, you can say that, okay, I want to render all trees up to 1000 meter distance and all rock up to 10 meter distance. Yeah. This can also help reducing the number of draw calls. Now, the camera component is not, also at least for the camera that is in my head right now, this component is not exposed in Udon, okay, for the player camera I mean, but VRChat released recently the VRC camera settings API, and here you can also play around with the layer curl systems of a player. Occlusion culling. So, occlusion culling is another culling method Unity support, but this time some setup is required. It basically culls objects that are hidden behind surfaces. First of all, we need to mark occluders, so objects that block others, as occluder static, and mark occludees, so objects that can be hidden, as occludee static. Then we can open the occlusion culling window and click on bake. Now, how does occlusion culling actually work? Well, basically Unity will spend a little bit of time on the CPU to figure out if an object actually needs to be rendered using the occlusion data we baked. If Unity notices that the object is not visible, then it will be removed from a list of draw calls, which improves performance. Now, be careful with very open areas, because in very open areas, like a forest, it rarely happens that an object hides another object. For instance, a tree doesn't usually hide another tree. Okay, in this case, occlusion can actually make the performance even worse, because Unity will spend a little bit of time figuring out if an object actually needs to be rendered, only to notice that everything needs to be rendered. So in this case, we have some wasted CPU performance. Now, on a side note, occlusion culling also slightly increases the build size depending on how precise you baked the occlusion data, but that's an issue I personally didn't really had yet. Now, manual culling. Actually pretty interesting. So basically it's possible to toggle objects with your scripts. The issue is that there's just some stuff you need to be a bit careful about. For instance, avatar stations. You can, if you want to, toggle on and off objects with events like on player trigger enter and on trigger exit. But if someone is sitting on avatar station, that player collider gets turned off. Meaning that when the player goes through the collider while sitting on an avatar station, it can be also just a regular void station. Then the event won't be triggered. And that's a bit annoying. I've seen a lot of voids that had this issue where suddenly things don't get culled correctly because they used on player trigger enter, on player trigger exit, and someone was sitting on station. It can easily happen. As a workaround, you can do distance-based object toggle. Basically, you check every X frames if someone is close to an object. That's not very performant because it requires scripting. You could also implement your own custom player collider, basically attaching a collider to the player every frame. That's also not performant. Or you can work with LODs to cull objects, which is the solution I would personally do because it's easier, more performant, and it doesn't require any Udon scripting. Oh boy, overdraw. Okay, I'm going to talk about overdraw for the next 15 minutes because that stuff can really kill performance, especially on the GPU. I'm just going to drink some water for a second. Just need to find my water bottle. Okay, I wish my headset has pass-through. I can't see shit right now. Anyway. Okay. Okay, overdraw. Well, basically, let's assume you render a pixel, you texture a pixel at the 24th draw call. But at the 37th draw call, the pixel gets retextured again. Well, you gave some useless work to the GPU, and that's what overdraw is. It's not something we can always avoid, like pretty much every board has overdraw, that's perfectly fine, but if there's too much overdraw, you're just giving too much work to the GPU, and that's not ideal. So overdraw affects the performance on GPU, contrary to draw calls that affects the performance on the CPU. Yeah? So, to explain a bit how overdraw works and how it happens, here's a little scene I created. It's basically an avatar standing in front of a wall. And I'm going to render this scene in two different ways. So I will do two simulations. In the first simulation, I'm going to render the wall first. In the second simulation, I'm going to render the avatar first. And for now, I will only focus on opaque materials because overdraw can also happen with opaque materials. Well, what happens if we render the wall first? Well, first the wall gets textured, and then the avatar. But then the avatar is going to retexturing pixels that were previously rendered by the wall, and we have overdraw because multiple pixels got retextured twice. But what happens if you do the opposite? If you texture the avatar first, well, first the avatar gets textured, okay. But now the wall gets textured. And here's the interesting thing. Here the GPU, for each pixel of the wall, the GPU checks if there's a pixel already in front of it. If there's a pixel already in front of it, then the pixel that is currently getting rendered gets discarded, gets thrown away. And that stops the rendering process of that texture. Of that pixel, I mean. The key point here is that this step happens before the pixel gets textured. Well, what does it mean? Well, it means that to have the least amount of overdraw, we want to ensure that the pixels that are the closest to the camera gets textured first, to ensure that the pixels that are further behind get thrown away. But how can we actually do that? Well, it's getting a bit complicated. The thing is, the GPU doesn't sort pixels on its own. Like, it doesn't sort the polygons also. Like, it renders all the polygons in the order they appear in the mesh data. and it also renders all the draw calls in the order it gets them. But which means that, well, if the GPU doesn't do any kind of sorting, it's the CPU who needs to do it, which means Unity. So how does Unity actually sort all those pixels? Well, basically it doesn't sort the pixels, but it sorts draw calls. Now, you may have seen in the material settings, there's something that says render queue, and here you can basically control the render order. So basically, Unity will first sort each draw call based on the material's render queue. The smaller render queues get rendered first, the higher render queues get rendered later. If multiple materials share the same render queue, then Unity will use the default sorting method. So it works like this. First, Unity renders the opaque geometries, the opaque shaders. Those get sorted front to back. The closest draw calls get rendered first, the further draw calls get rendered later. In my particular case, this podium in front of me is the closest to me, but gets rendered first. Backs here, there are a bunch of avatars, they get rendered a little bit later. The bookshelves are way back there, they get rendered pretty much last. And then at the very end, the skybox, which has technically a render queue of 2500. Now, after the skybox is rendered, all the transparent materials get rendered, and they have technically a render queue above 3000. Now, because transparent materials are rendered after the skybox, it means that transparent materials overdraw. Okay. Now, that's how Unity sorts draw calls, just by using the bounding box center of the mesh, and it calculates the distance between the camera and the bounding box center of a mesh, which usually is good enough. But it can sometimes cause some issues. And here's like a little example. So I created here this room here, which has just a little picture frame in it. Now the player is very close to the bounding box center of the room. Now here the issue is that because the player is very close to the bounding box center of the room, Unity will say that I need to render the room first. And that's something we can see in the frame debugger. When I select one draw call, we can see the room gets rendered, and on the next draw call, the picture frame gets rendered. So here the picture frame is overwriting some pixels that are previously textured by the room. I'm going to show you two ways how we can fix that issue. The first way will be to separate the wall into a separate mesh. This way we have three separate bounding boxes. We have the room bounding box, the wall bounding box, and the picture frame. This is something Unity can very easily sort front to back, okay? Now, as a side note, I had to turn off static batching on the wall on the back to ensure that it doesn't get merged back together to the room, because if it gets merged back together with the room, you have two meshes again, the room and the picture frame, and we're back to square one. So here I turn off static batching on the wall and back. So in this particular case, I have one more draw call, but less overdraw. Is it worth it in this particular case? Probably not, because it's a very simple scene. But it can be useful sometimes to know about it. There's a second solution. This is the solution I would recommend. In this particular case, it's just increasing the render queue of the wall. If I set the render queue of the wall to, for instance, 2005, 2000 before being the default value for opaque geometry, well, then the room gets rendered later, and we can see it in the frame debugger. So we can see that first the picture frame gets rendered. In the next picture, we can see that the wall gets rendered. So here we have front to back sorting, everything is sorted properly, and we have no more overdraw issue. Now, hidden geometry can also heavily affect the performance of VRChat words. I had that issue a lot. It's very annoying. So, to show you how hidden geometry affects the performance, I created this mesh here, which is basically just the plane in which I applied an array modifier on it, and I applied it 10,000 times. So it looks like a cube, but in reality it's more like a book. It's like 10,000 overlapping planes. And I created two versions of that mesh. In the first version, I created just a regular mesh. I just exported it like this, And in the second version, I just flipped the normals. And I exported that. So I just flipped the normals, that's it. So the one where I didn't flip the normals, I had 50 FPS. And where I flipped the normals, I had 600 FPS. It's pretty interesting. Like, the mesh itself didn't change, but just because I flipped the normals, I had 600 FPS. Also, side note, I forgot to say that, but because I flipped the normals, the mesh is actually pointing the other direction, so I actually had to place the camera behind to actually see the mesh, And that's the only difference. Yeah, this might sound surprising, huh? But actually the reason is actually pretty simple. So for the mesh on the left, we were really unlucky. All the faces got rendered back to front. So huge amount of overdraw. For a mesh on the right, well, basically because I flipped the normals, I need to look at the mesh from behind. And because I'm looking at the mesh from behind, suddenly back to front becomes front to back. And here, no more overdraw issue. Now, what I'm trying to explain here is not that you should flip the normals. It has absolutely nothing to do with it. But what I'm trying to explain here is that we have pretty much no control over how the GPU renders the mesh. It gets rendered in, the GPU renders all polygons in the orders they appear in the mesh data. And we can't really control the mesh data. I had that issue also with thin geometry in a lot of my VRChat words. On the right, we can see an example. So here I used FPS VR, which shows the GPU frame time and the CPU frame time. And here the GPU frame time, yeah, I mean, we see it's like red, it's really suffering, and the CPU was just chilling. It's kind of like in some, in some group projects where one person does everything, or one is just a mole support, I guess. So here the CPU sent the 10 draw calls to the GPU. Okay, come on, it's just a staircase, you can render it, but the GPU, oh boy, it was really suffering, huh? So how to avoid hidden geometry? Well, basically you can modify the mesh in Blender if you want to delete hidden faces. Just on a side note, you may think that cutout shaders can also kind of delete geometry because, I mean, it makes faces transparent. So you may think that, oh, it's not rendered anymore. No, that's not true. Cutout shaders are actually terrible for performance. Don't do that. And there's no solution I will explain in the next slide. Now let's take this cube I created, this Boko. Let's call it the overdraw cube or the lag cube. And let's just separate it into 5 separate meshes. Now, because I separated it into 5 separate meshes, Unity can sort each face front to back. Now, each polygon in that object might still be rendered back to front, which would still cause overdraw. But what's actually going to happen here is that Unity will render the closest object first, and then the object behind it. But now there are pixels already in front of it, so the meshes behind, they don't get textured, so we have less overdraw. And just by separating this mesh into 5 separate meshes, I notice huge performance improvements. Be careful if you use static batching, because here Unity will merge everything back together into a single mesh, and here front to back sorting is not ensured anymore. GPU instancing, on the other hand, is actually much better, because with GPU instancing, Unity knows where the player is located and can actually sort each instance front to back. So with GPU instancing, you have usually less overdraw. A possible use case would be if you're like inside a train and you're looking at a bunch of seats. Let's just assume all the seats are a single mesh. And let's just assume you're like in the front of a train and you're looking behind you. So all the seats, if you look very little, like all the seats get rendered back to front and you have huge amount of overdraw. But then when you go in the back on the train and looking in front of you, suddenly back to front because front to back, and you have better performance. So that's actually the weird thing about the overdraw. Like sometimes you can have good performance, but then when you go in the different spot of the world and look behind you, and then you have terrible performance because of overdraw. So what I will do personally here in this particular case would be to separate each chair into a separate mesh. By doing so, basically each chair is technically the same mesh, so we can use GPU instancing. And if you use GPU instancing, Unity can sort each of those instances front to back and pretty efficiently, so you might have less overdraw. And also if you use GPU instancing, it will also decrease the build size because you don't need to static batch it. You could also technically use static batching, but just be careful with what I explained before. Unity might static batch the seat that is the closest to a player with the seat that is the furthest away from a player, and that is not really great for front to back sorting. But if you use the editor tool I mentioned previously, where things get batched together by distance, it's much better. Yeah. Okay, LOD, level of detail. Now, I don't want to spend too much time talking of LODs because I think most of you already know what LODs are, and also want to have some time for a Q&A at the end. But basically, LODs can improve your performance in a few ways. First of all, reduce the amount of polygons on further away objects. Like the GPU really doesn't like to render micro triangles. It's a lot of wasted performance, so it should be avoided. We can either make our own LODs using Blender or generate them using editor tools. LODs can also help reducing the number of draw calls, because with an LOD component, you can also cull objects at a certain distance. And here you don't need to use editor tools. And that's personally what I use mostly the LOD component for. Now, VRChat has an LOD graphic setting. I usually have my LOD settings set to low, and sometimes in some VRChat voice I saw objects popping in front of me and at like 1 meter distance, which isn't great. So I would highly recommend testing your LODs with different settings to make sure your LODs work properly. Here are a few ideas you can do to do nice LODs. First of all, you can disable some shader features on further away objects. For instance, you can have like the most amazing shader, tree trunk shader, like that has normal map and I don't know, a bunch of stuff. But when the tree trunk is like, let's say, I don't know, 10 meters, 50 meters away, you don't see that stuff anymore. So you can just switch to a more optimized shader that has some shader features disabled. You can cull smaller objects sooner, like small rocks. You don't need to render them at 1 kilometer distance. Just hide them after maybe 10 meters or so. You can also use totally different shaders. Like for instance, you can have a glass cup, and when the glass cup is further away, you can switch to an opaque material, opaque shader. Also reduces the amount of overdraw caused by transparent shaders. You can also tree leaves usually use cutout shaders, so to minimize the amount of overdraw caused by cutouts, you can delete some tree leaves on further away trees. So basically, reduce the amount of overlapping geometry. And you can also talk about something else. You can also use something else, which is billboards, which I will talk about the next slide. Impostors. Now, thanks to VRChat, I think we all know what impostors are. It's basically those avatars we can generate if we are too lazy to make our avatar quest compatible, or at least that's how I use impostors. But it's actually not something VRChat invented. They have been used in games for years, and the really cool thing about impostors is that you have probably seen impostors in games before, without realizing it. And that's why they're called impostors. So impostors are basically fancier billboards, and they show a different image based on the angle we are looking at, to give the illusion that we're looking at an actual mesh. But in reality, they are just 2 polygon planes, similar to a billboard. On the right, we can see an example of a texture I generated using editor tool. So basically I use an editor tool that takes a picture of a mesh from different angles. And the result is that it generates an atlas you can see on the right. Now, this is how an imposter would look like on a tree, what I generated. Now, I know what you're thinking, it's ugly, the tree is like very pixelated, but you know, it's an imposter, it's supposed to be generated from far away, and from far away, this is how it looks like. Like here, it's barely, yeah, it's pretty much the same thing. And that's a really cool thing about imposters. Now, I did also some benchmarks with a tree I had, which has 455 triangles, and the imposter, which has 2 triangles. And we can see that with imposter, I have the better performance. I went from 260 to 270 FPS. Now you may notice something that the performance is actually better, but not by much actually, just 10 FPS. And the reason is for multiple reasons. First of all, imposter shader I was using. There might be more optimized shaders out there, but the one I was using, I mean, has a lot of functionalities. And also the second reason is because the imposter shader is a cutout shader. Now it's not visible on the picture, but the tree is actually a pretty big quad. So there are a lot of transparent pixels, and when there are a lot of transparent pixels, that's where cutout shaders actually perform the worst. Let's say the spider web. The spider web is basically just 2 lines on a quad. Most pixels are transparent. That's where cutout shaders perform the worst. And here, it's not as bad as a spider web, but there are still a lot of transparent pixels. So there's a lot of wasted performance here, a lot of overdraw. Okay, optimizing Udon code. Now, I don't want to spend too much time talking about Udon because Happy Robot already did an excellent presentation last year. I highly recommend to check it out. It's on Firon's YouTube channel. It's called Firon Umbra Udon Development from First Step to Optimization. But to summarize, Udon is slow. When I benchmarked Udon, I noticed that it was between 500 and 1000 times slower than regular C#, and this was for a script that wasn't very math heavy. So for math heavy operations, it can be even worse performance wise. So basically, to optimize Udon code, it means you should run less code every frame. Ask yourself a question if you really need to execute code every frame. Prioritize custom update loops, which calls itself every X amount of seconds, which we can see on the screenshot. It's basically just a method called custom root, which calls itself every 1 second. Use more built-in Unity features. For instance, moving object using animator can sometimes still be more performant than moving it in Udon. You can also move object using a nav mesh. That's also a way to move objects using built-in Unity tools. You could also move objects using rigid bodies, which is something I did in my virtual park VOD. So I actually have a few code examples in my full presentation. Yeah. You can also disable scripts that don't always need to run. For instance, a clock. If you're outside the home, the clock doesn't need to run, so you could technically disable the clock script in that case. Now, some tasks can also be moved to a GPU. For instance, billboard effects should be done on the GPU if possible. Like I've seen sometimes people doing billboard shaders, billboard effects in Udon. And by I've seen people, I mean I've seen myself doing it, because back then I didn't know anything about shader programming. I did billboard effects in Udon, which is really terrible for performance. Don't do that, please. And lastly, Udon behaviors are by default networked objects. So even if they aren't syncing anything, and this which adds additional CPU overhead. So if you have, for instance, a mirror button in a VOD, make sure the syncing method is set to none instead of continuous or manual. That saves a bit of performance, especially if you have thousands of scripts in your VOD, which, I mean, sounds a lot, but that value can quickly be reached if gain VODs or VODs that uses a lot of prefabs. Okay, to summarize. Okay, draw calls affects the performance on the CPU. So to reduce the number of draw calls, you want to use static batching or GPU instancing. Bake your lightings to reduce the number of real-time lights and shadows in the scene. Reduce material counts either by using atlasing, trim sheets, or custom shaders that basically blends between different textures. Overdraw affects the performance on the GPU. So here use the initer tool to figure out to check if all the draw calls get rendered front to back. Okay. Avoid hidden geometry. Also very important. That's like the kind of hidden draw call you cannot really debug using a frame debugger. So if you have hidden geometry, delete all that hidden geometry if you can. Use LODs to reduce the polygon count on further away objects. Occlusion culling in more enclosed space. Doesn't work well in more open areas, something to be careful about. And avoid execute Udon code every frame. Thanks everyone for watching. So, like I said, the full presentation can be downloaded on my GitHub. I don't remember if I said at the start of the presentation, but when I was working with this presentation, I had 90 slides. This presentation here has 47 slides, so I had to delete a lot of slides just to fit it inside the 45-55 minute time frame. So the full presentation, the 90-slide presentation, can be downloaded on my GitHub, which goes more into details about a lot of things I explained during this talk. And yeah, thanks everyone for watching. I hope everyone learned something new today. And if you have any questions, my Discord is here. You can ask me directly in the Q&A channel. You can ping me. And if you see me in the VRChat VOD, you can also ask me questions in the VRChat VOD. Thank you very much. Yay.
Hello there.
Oh, here you are. Okay, I was looking for you.
I've got a bunch of questions from the audience here. Let's see. I've got one here from NitroWolf902. As a 3D game artist in college, I'm still confused on batches. I want to make VRChat worlds that look very good, but are heavily optimized. I've done texture atlasing and baking low poly models, but I'd like to take that further. Any suggestions?
Oh, yeah, that's an interesting question. Huh? So here I will just play around with usually what I do here is just playing around with the Unity frame debugger and see how I can reduce the number of batches, etc. Now, for a VRChat point of view, I also try to reduce the build size. So, for instance, if there are like hundreds of trees in the scene or like dozens of trees in the scene, I try to avoid using static batching because that can actually pretty rapidly increase the build size. So here I will probably try to use GPU instancing. So also something I unfortunately didn't have time to talk about in a full presentation, but there are also ways to actually GPU instance meshes that seem to be different using some techniques called UV tile discard, which I have a few examples on the full presentation on my GitHub account. So basically what I did here is merge multiple meshes together into that seemingly different, like let's say a tree and a rock, and I put them together in Blender. And what I did is just using some kind of UV tile discard, I just hide the tree or hide the rock. And the UV tile discard property can be an instance property, which means that you can this way GPU instance a rock and a tree together. No, it's something I cannot really explain in like 1 minute how it works. But here I would just recommend looking at my full presentation on my GitHub account, and that's also a shader example you can try out. Actually, yeah. It's actually a pretty difficult question. Like there's a lot of things to, but yeah.
Go on.
Yeah.
All right. I've got another question here from Voxian. How are stencil shaders handled with overdraw and render queue?
Oh boy. Okay, I'll be really honest. I don't know. I'm still learning how to make shaders, so I don't know. Yeah. Yeah. Stencil, I'm not sure how they actually work, to be honest. Yeah, I'm sorry.
Let's see. Another question from Nitro, actually. It was related to your slide earlier about flipping normals. When you flip the normals, do you mean on the outside so the camera sees it, or it doesn't?
So basically, let's say all the faces are pointing this direction. When I flip the normals, all the faces are now pointing this direction here. But because the camera is like looking this way here, well, because the normals are now looking this way, I basically need to place the camera here and not looking this way. So technically, it's like rotating the mesh 180 degrees, and that's it. And the interesting thing is that because I flipped the normals, the mesh data didn't technically change. So now when I look this way suddenly, well, all the faces, instead of getting rendered back to front, they get rendered front to back. And in this particular case, I had less overdraw issue. And that's basically what I try to explain here.
All right. Let's see. We've got another question here from Jack. You mentioned at the beginning that dynamic lights, in the worst case, double your draw calls. Doesn't that only apply to forward rendered materials? From my understanding, deferred materials aren't that bad with lights.
Yeah, it's something related to render passes. So basically, if a shader uses a forward additive pass, that's basically an additional draw call for each pixel light in the scene. So basically, in a PBR shader, you have the forward base pass, which handles everything related to colors, light maps, light props, etc., etc. But then you have a forward additive pass, which handles everything real-time light related, point light, spotlight, etc. So because of that forward additive pass, you get more draw calls if you have real-time lights. Yeah.
All right. Thank you for answering that. Let's see. We've got a question here from Maxwell Falth. With what you've shown today, how easy would you say is it to optimize a large world enough for it to be Quest compatible?
That's why, yeah. So it depends. The thing is, in a large world, could be, for instance, a forest, for instance. And the problem with forest is that trees, they have a lot of tree leaves, etc. That would, and for tree leaves, we usually use cutout shaders, but cutout shaders are really not great for mobile devices and really should be avoided because of the whole architecture, of the whole mobile GPU architecture. They use TBR tile-based renderers, and cutout shaders doesn't work so well on those mobile devices. I will just avoid using cutout shaders, mostly just use like simple geometry, simple tree geometry. Also heavily work with LODs, like hide objects a bit sooner, I would say. Problem is also that with open world areas, we cannot really work with occlusion culling. So we really have to work with LODs, low poly count, no cutout shaders, etc. So, like the example I showed with impostors, I wouldn't use that in a Quest compatible world personally, especially if there are a lot of objects.
All right. Got another question here from Valen. Hope I pronounced that right. How much do particle systems affect performance? Any tips to improve them?
Yeah, problem with particles, it's a bit of CPU work. So yeah, it's also particles. It's also overdraw because they use also transparent materials. I will just try to reduce the number of particles. Let's say you don't want to render 10,000 particles at once, maybe just 1,000 or so. And GPU instancing can also be nice to reduce the number of draw calls. I would also try to turn that on. That's basically it. The issue with particles is just that you can very quickly have a huge amount of overdraw because of all the transparent materials overlapping each other. I would just reduce the amount of particles personally, yeah, and just try to make it look good, and also try to keep it performant. Yeah, it's actually a tough question. I had that issue also a few times.
I've got a question here from Laridon.
Yeah.
Have you experimented with the new VRC light volume systems that was released recently? Do you have any thoughts on it? If yes,
I've experimented a little bit around it, but to be honest, I don't know much about how it works. It's really nice, actually. I've heard that it's maybe slightly less, at least from what I've heard, apparently it's less performant, a little bit less performance like props, but it looks so much better. So I would definitely use that in my VRChat votes. Definitely worth giving a shot. And also I saw it's not released yet, but apparently it's implemented some kind of system that kind of simulates real-time likes. I have absolutely no idea how that works. For me, it's like kind of like shader magic here at this point. Yeah, definitely very interesting. Definitely something I would like to play around, but I cannot give any recommendations because I don't know much about it. I guess you will have to ask Red Sim about it. Yeah, one who created that prefab.
All right, thank you for answering that. Got a question here for Enverex. Any thoughts on dynamic batching? You mentioned static batching and GPU instancing, but not dynamic.
Yes. So the issue with dynamic batching is basically like static batching, but it's done at runtime. So basically what Unity will do is merge meshes together, similar to how static batching works, but at runtime. But the issue is that merging meshes together at runtime has sometimes a higher overhead than the overhead of a draw call. So with dynamic batching, especially if a mesh is low poly, let's say a quad, no, high poly, I'm sorry, opposite. Especially if a mesh is more higher poly, like let's say 100 vertices, 100 polygons, then Unity will merge those meshes together. But it takes a lot of time for Unity to actually merge them. So you will actually get less draw calls, but the performance will actually be worse. So personally, the only time I noticed that dynamic batching was actually improving performance was with quads. But I would personally just use GPU instancing because the performance improvement I noticed was maybe like 20-30% or so. With GPU instancing, it's like 200% improvement. So that's why I actually didn't talk about dynamic batching because I don't like it. And also when I saw in the Unity documentation, they don't even recommend it anymore. Yeah, maybe it's a legacy feature. I'm not sure, but yeah.
All right. I've got another question here from Eric Bazinga. When it comes to splitting meshes and occlusion, I've seen both used together, but what's some cases where you'd want to avoid one or the other? Wouldn't splitting the mesh for occlusion increase the number of draw calls?
Splitting the mesh for occlusion. I guess like it's like the case where, for instance, every room in a house is like a single mesh versus where every room is a separate mesh, I guess. Well, the thing is, in that case, I would personally separate each room into a separate mesh, mostly because of overdraw. Because if everything is a single mesh, well, you don't know really how the GPU is actually rendering all those rooms, and that can cause some overdraw. And by separating into different meshes, well, first of all, occlusion culling is actually going to work. I think I forgot to say that during the presentation, but yeah, occlusion culling doesn't work if everything is a single mesh. So if every room is like a separate mesh, then occlusion culling can work pretty efficiently. So it might increase the number of draw calls, but probably not by much. So yeah, I would definitely do something like separating each room into a separate mesh. Yeah.
Okay. I think we have enough time for one more question here.
Okay.
Let's see, from Game Killer 48. Grass seems like a curse. Cutout textures are bad, but so are high poly counts. What is the suggested approach for grass in VRChat?
Yeah, that's also a tough one, actually. Yeah, like you're right. Like cutout shaders are very bad for performance. They cause overdraw issues, especially if both pixels are transparent. I would personally just decrease the render distance of grass. Like you can make some really nice textures that look really nice even from further away, which blends nicely with the grass on the foreground. That's actually something also I try to figure out myself, how to render grass. It's not an easy subject actually. Yeah? It's actually a very interesting question. But I will just try to reduce the amount of overlapping geometry. Basically, that's personally what I would try to do. And yeah. Getting some very interesting questions,
I
actually.
think that's all the questions we had.
Yeah.
You want to say your outro here?
Yeah, thanks for watching. Hope everyone's enjoying VRChat so far. And hope everyone learned something new today. And yeah, see ya.